In this lesson, we're going to discuss exponential decay functions. So exponential decay functions are almost identical to the setup of exponential growth functions. If you can do an exponential growth function, you can do an exponential decay function. The primary thing I want to point out about an exponential decay function is what the value of b here is. So our base has to be a value between 0 and 1, not including 0 or 1. So we're talking about values like 1/2, 1/3, 2/5, or even as a decimal, 0.3. So if you have a b value that's between 0 or 1, then it's going to take on a slightly different characteristic. Instead of curving up, it has this tendency to curve down like so. And one of the things that I want you to notice about this is that it still goes through the point 0, 1 on the y-axis, so it has a y-intercept of 1, and you still have the value of 1b, where b is the base. So if your base is 1/2, then that's going to go through the point 1, 1/2. And then you transform it appropriately. If you're dealing with a vertical stretch or shrink with your value of a, you deal with that. And of course, your h and k work the same way as this. So that's, in a nutshell, the exponential decay function. Don't forget, these also have a asymptote that runs along the x-axis as well. The other thing I want to talk about is what the exponential decay model is. So basically, if something is going to be decreasing by a certain amount, a percentage each year, we can model that with this exponential decay equation, where it's y equals a 1 minus r to the t power, where again, our a value is the initial amount, but this could be anything. It's not restricted to money like we do with the compound interest formula in the previous section. And so there's our a value, and then r is our percent decrease. So again, we'll write this as a decimal, but what we call this whole unit of 1 minus r, this is known as the decay factor. And the decay factor is just kind of the total amount of decay. So why is it that we subtract it from 1? Okay, I want you to think about that. Why is that it was 1 minus r? And what does this new value mean? Ask that in class, and we can discuss that. The next thing is our t, and again, we already know what t is. We've done this before. It's the amount of time used when you can decay. Usually, this quantity is in t years. So in our example, we'll say a new car costs $25,000 and the value of the car decreases by 15% each year, and we want to estimate that value after 4 years. So the way we would set that up, we would say y is equal to our initial amount, $25,000, times 1 minus r, which is a percentage, which we express as a decimal, 0.15, and then to the 4th power 4 years. When I work that out, when I say 1 minus 0.15, that's going to leave me with 0.85. That's my decay factor. Sometimes we get a problem that asks what the decay factor is. So what does that mean really? And then we can just punch the remainder of this in the calculator and see what that is. We should get y equals 13,050 and 16 cents, we'll say approximately equals that amount. So then we would say, therefore, the car would be worth about, it's just not working, about $13,050.16. Just not writing correctly. Okay, so anyway, that's it. You can do exponential growth, you can do exponential decay. Until next time, I'll see you on the flip side.